Welcome back, guys, to another episode of Calc A, B, and BC Prep. Now today we'll be going over chapter 4.2 in my textbook, which is about the mean value theorem. Now basically what the mean value theorem allows us to do is sort of connect our average rate of change to the instantaneous rate of change over a closed interval. Now formally in the textbook, it says that if a function of x is continuous at every point of the closed interval, AB, and differentiable at every point of the interior of AB, then there's at least one point C in AB where the derivative at point C is equal to the slope between points A and B. So this is our instantaneous rate of change at a certain point in the interior of AB is equal to our average rate of change. Now the two things that you really need to remember before you do any math relating to the theorem is that the theorem is only satisfied if the function is continuous in the interval and differentiable at every point within the interval. Now the way you check this is that first you check the domain of your original function and make sure the domain fits the criteria of your closed interval. Next, to check if it's differentiable at every point, you first take the derivative of your function f prime x and make sure that f prime x has a domain that fits within the interval. Now if you meet these two conditions, then you can apply mean value theorem. So over here is a little example to visually show what it means. So I have a function here, f of x equals x squared, with a domain from 0 to 2 closed. So the the slope between points 0 and 2, which is like our a and b, if we were to apply it to the mean value theorem, we have f of 2 minus f of 0 over 2 minus 0 equals, well, f of 2 is 2 squared is 4 minus 0 squared is 0 over 2 equals 2. Now this is our average rate of change, but according to the theorem, there must be a point C within this domain that also has an instantaneous rate of change of 2. So that means this must also equal our f prime of C. Now if you took the derivative of the function x, we have f prime x equals 2x. So that means f prime C is equal to 2c. Now, from our definition of the theorem, f prime c, which is 2c, is equal to our average rate of change, which we calculate it as 2. Therefore, if you want to know the actual point of c, it's 2 divided 2 is 1. So our value on the horizontal axis, c, would be 1. And at x equals 1, both the average rate of change in the interval and the instantaneous rate of change would have a slope of 2. Now over here in the bottom, we have a specific type of mean value theorem, I guess. It's referred to as Rolle's theorem. Now what Rolle's theorem says is basically the same thing as the mean value theorem, except it's a specific case where, so it has to meet those first two conditions of being continuous and differentiable, but also it says that f of a must equal f of b. And if it does that, then f prime c will equal 0. Meaning the slope of the tangent within the interval will be 0, which makes sense because if two things are at the same, y value in the interval, they're equal, then their slope would be 0. So that means the tangent within the interval would also have a common slope, according to our mean value theorem, which would also be 0. And just on a side note, this kind of relates back to the previous chapter, 4.1, where remember we said that critical points must either be where the derivative equals 0 or it's undefined. So if Rolle's theorem applies, that means somewhere the point C has a tangent slope of 0, meaning it is possibly a critical point and a extreme value. So just a little side note there. And now we can apply the principle of the mean value theorem to actually prove the definitions of an increasing and decreasing function. So within an interval I that satisfies the conditions mentioned before, if a function increases on interval I under the fact that x1 is less than x2 and f of x1 is less than f of x2, meaning y1 is less than y2, then the function is increasing. So if x1 is less than x2 and f x1 is less than x2, then that makes sense that the function is increasing. Now, for a function that's decreasing, if x1 is less than x2 and f of x1 is greater than x2, we'd see that it is definitely decreasing. Now, the way you could prove this with the mean value theorem is saying that positive derivatives indicate a increasing function. So if f prime is greater than 0 at each point in the interval AB, then the function increases within the closed interval. So if I just had the derivative of c equals the average rate of change between x1 and x2, then we'd apply the mean value theorem. So we know that x2 is greater than x1, so the bottom will always be greater than 0 or positive. And we know that we're trying to prove that the derivative, we know that the derivative is, when it's greater than 0, it's increasing. So the derivative must also be positive. Well, if we want the whole thing overall to be positive, that means our y values must come out to be greater than 0 as well, so that both of them are positive and make our derivative positive. So then we'd solve and we get f of x2 minus f of x1 must be greater than 0. And if we solve, we get f of x2 is greater than f of x1, which if we just flipped, we get is less than f of x2, which is exactly what we have written over here. Same principle follows here. If it, this time though is kind of the opposite. So if f prime c equals the average rate of change between the 2 points, this time, however, we want the derivative to be negative, so it must be less than 0. Now we know the bottom will still always be positive because x2 is greater than x1. So the only way we'd have a derivative that's negative is if our top is also less than 0. So we're going to solve so that it is less than 0. We get f of x2 is less than f of x1, and we could switch that around, get f of x1 is greater than f of x2, which is exactly, again, what we have over here. And that is how you prove the definitions of an increasing and decreasing function using the theorem. Now over here we have 2 more facts that are mentioned in this section. So if the derivative f of prime x is equal to 0 at each point of an interval, then there's a constant c in which for all x values in the interval, f of x equals c. This is basically saying that if we have a line with a bunch of points and the derivative is always 0, that means we basically just have a flat horizontal line, and that means if we were to graph it, the function would just be y equals a constant value, which makes sense. But if we were to prove it analytically, we'd show that the f prime x equals f of b minus f of a over b minus a, which is again the mean value theorem. Now we want f prime x to be 0, so 0 equals b minus f of a over b minus a, and if you cross multiply this, the bottom becomes 0, so 0 equals f of b minus f of a, hence f of a equals f of b. So if the y values are equal, then of course the slope between them will be 0. And then this condition meets for every single point where they're on the same level for y, then they definitely have a slope of 0, hence how we prove fact number 1. So fact number 2 builds on the idea of fact number 1. It says that if f prime of x equals g prime of x at each point in an interval, then there's a constant c in which for all x values in the interval, f of x equals g of x plus c, which probably makes obvious sense to you, where if we have 2 functions with the same slope at every single point, or the same derivative at every single point, that means they are parallel to each other. So let's try to prove this analytically though, using what we know and fact number 1. So let's say we have an overall function h of x equals f of x minus g of x. Now if we took the derivative, we would get h prime x equals f prime x minus g prime x. Now if f prime x is equal to g prime x at every single point, that means they cancel out and equal to 0. Hence h prime of x must also equal 0. Now this is where we refer back to fact 1, where we realize that if the derivative is 0 at every single point, then the actual function original function would be f of x equals c. So that means h of x is equal to a constant, which makes sense because if we work back again, we know the derivative of a constant is always going to be 0. So now we refer back to our original from above, where we found that, h of x equals f of x minus g of x. We know that h of x is c, so c equals f of x minus g of x. And if we rearranged it, we'd get f of x equals g of x plus c, which is what the fact number 2 says. And yeah, that's pretty much it for this episode. We covered mean value theorem in chapter 4.2, and 4.3 will be soon to come with the derivative tests. So yeah, see you guys later.